I will share our presentation. For a moment, please.
Yes, we can see the presentation, Mr. Rusnandi.
Yeah, thank you very much. Yeah, the presentation maybe will be held by Vinh from Vietnam, because I have do some research and then implementation and development about the water treatment plant based on the surface water treatment, and then also I'm focusing to the colloid and to the colloidal and flock development. Okay, what the microhydraulic I call the microhydraulic water treatment plant technology. This is I have already patented, yeah, with 2 patent registered, and then one about the methodology, and the second about the mobile water treatment plant. And we are really focused only to the colloid and to the flock development, because I think this is really will help. First, I make water more clear, and then after clear, maybe for polishing, maybe for another pollutant. I call here maybe, yeah, with we say about the successfully, but the successfully I think, and my research. This is I'm already research, and then I already working for the water treatment maybe since 1985. At the time, first time I'm working with Iwaco BV, yeah, from Netherlands company as a consultant, and then after that joined with Royal Haskoning and another. My research and my implementation, I have now how to make a treatment plant more efficient. The production capacity possible can increase until 250% with the same dimension and the same sorry. Okay, thank you. Yes, the production capacity possible increase until 250%, and also the coagulant or chemical dose possible to decrease until 50%. My target for this research and then for implementation of the treatment plan, this is in the effluent of clarifier. The effluent of clarifier almost 0 NTU. This is more better and more important for how to process after will be more better for the filter, for the everything will be more efficient. Also, for rapid sand filter cell, this is possible running until 72 hours or 3 days. Yeah. Also, the electrical consumption will be less because we have no need the electrical mechanical system, especially for mixing system, and also if dosing, sorry, and also it for the backwash system, if needed pump, the pump just running maybe very very long. Yeah, I mean only every 72 hours. This is maybe what the achievement of microhydraulic, maybe, yeah, now is proven technology for implementation of for utility in Indonesia and in Vietnam. and also can to treat and in tropical water, yeah, in extreme turbidity and sludge load, and also very efficient in chemical and energy. Average skill required is not needed to more high level. This is just operator. And then also the key of innovation in the coagulation and flocculation. Also innovation, the development in 3D model, and then trial run for calibration and use 3D model for real life design. And also we have example here for Indonesia and Vietnam, and also for emergency plan. This is I'm explain first about the our experience, how a treatment plan work. Yes, this is really maybe can I can show in the left. This is in the first time commissioning the plant in Vietnam. This is coagulation flocculation only. Yeah, this one is very clear in the clarifier. Yeah, this one. Another one, maybe this is, I try with 2 slide. Maybe, sorry, this is only double. This is another video, also in Vietnam. I can try. Yeah. This is flocculation system. Yeah, this is also in the clarifier. In clarifier, almost the turbidity almost 0. Okay. Now another plant in Indonesia, we have I'm lucky here. I can try in many plants in Indonesia to build new one and to rehabilitation. One this plant, I have order from Ministry Public Work and then a water company in Indonesia in Makassar. They ask about 70 liter per second, but after commissioning we have 150 liter per second. So sorry, the unit Indonesia commonly we use a liter per second. This is video. This video I want to show you. This is we have 5 chamber or 6 chamber with coagulation and flocculation. This is chamber number 1, and then you can see this is chamber number 1 and number 2, and this is number 3. This is the flock is very this is number 4, 3, 4. Oh, this is this is the final flocculation. You can see the flock is really gentle and then really very good. And going to the clarifier. Yeah, I just passed. If we see the chamber number 1, this is the first flocculation. Chamber number 2, chamber number 3, chamber number 4, 5, and 6. This is a final flocculation. This is really everything is already with a very good flock. This is also our experience in Bali. I have designed and built very dirty or very turbid water. I think maybe everybody will know how big the turbidity is. I think turbidity is very high. Yes, almost maybe 1,000 NTU. But you can see this is raw water, and then raw water coming to the clarifier. This in the side, this is clarified directly, from clarifier going to the filtration, or in influence of filtration. This is very clear. The turbidity here is really almost 0. Okay, the plant not only built in steel construction or stainless construction, also I try in the concrete. This is very simple treatment plan. You can see this is the flow collection system, only 5 chamber, and then beside you can see this is the flow collection, and then beside is the clarifier, is really clear. Other one. Also, the microhydraulic already implemented to the mobile water treatment plant, and then already try in many disaster. Let's say here is a sample disaster in Jakarta during flooded in there, yes, in 2013, and then many time also. The raw water coming from the flood water self, and then this is the result of the treated water for help to people around. This is one example. The existing, I don't know who already built, yes, but you can see here the clarifier, many clarifier like here in Indonesia. Yes, that is the one introduction about our microhydraulic. I want to explain very fast, maybe now, but by my history, I have experience in 1985. Yes, we have so many problem during commissioning. Let's say about the commissioning for the new treatment plant. That is really problem to set up the first time. Also, if we know about how to do the jar test. In my experience, we can do the jar test. Possible detention time about 5 until 10 minutes. It is very good flow we can found. But in the theory on the standard and everything, they said maybe the standard of detention time more than, let's say 30 minutes or even maybe 1 hour. But I can reduce about 5 until 10 minutes. Also, the coagulant dose. The coagulant dose also still make a problem for the plant, because the coagulant dose not really mix in 1 second, but sometimes also coagulant goes too many coagulant, and then will be zero. Will be not. Will be neutral, maybe after floculation or after sedimentation. This is also sometime in Indonesia, in Jakarta or in Bandung. Sometime coagulant already still we can found also in the bathtub or in the bath at home. And also about the design criteria or detention time. Yeah. This is also design criteria. Sometimes we have a standard in Indonesia about design criteria. They said about detention time and another. Yeah. Also the capacity, production capacity. From this problem, I think many times, maybe let's say about 15 or 20 years. Yes, I just thinking about how to looking for the solution. Let's say before, say about water supply goals for in the past in IGGI, CGI, and MDG. In the future, maybe for the SDG. Yeah, from the first time, I just thinking about the problem coming from fast mixing and slow mixing. After I try to make research and to make many measure and to try many model of plan, I found how the relation in between gradient velocity and detention time. The idealist must be look like the blue line, but in fact like the red line. This is the red line because this is not really smooth in between chamber of flow collision, sometimes flocculation just maybe connecting in between by pipe or connecting by gate. Yes. The good one of the flocculation, I think, because many type of flocculation. Let's say the name or the type, bevel channel or labyrinth or with rotary. But the good one, I think, the rest, the flocculation, the good one, I think, the typical is bevel channel, but very expensive and then need a very big space here. And after my research and my many time for trying and many time to make a model, I just found it is my pattern. The G is not needed really 1000. It's enough 500. The G 500 per second is okay. And then also the time 10 minutes is okay. But sometimes I make more better little bit high. This is our system in microhydraulic. That is, of course, you can see detention time now until 30. We have only 15. That is double. Yeah, capacity of course here it will be double. Now we try the research. The research microhydraulic I try since 2000 in ITB Delft. Of course, I'm a long time ago from ITB, yeah, from the era about 1978. Yeah. Everybody, I think, already know about what the component of the system treatment plan. You know from many information about what kind of the treatment plan component. It is raw water, dosing system or chemical dose, fast mixing and slow mixing, clarifier or sedimentation or filtration, and then the reservoir, and then the disinfectant. My focus only in dosing, coagulation, flocculation, and clarifier. This is more important for our research. Yeah. But of course, in every research, I have also look also for rapid set filter and disinfection. This is also during research, I try to study literature, mathematical model, and laboratory model and validation. Also, real pilot plan in real water treatment plant. This is lucky for me because I have so many help from Ministry of Public Work and so many water company also help me to build and to try. This is what the flocculation or the conventional water treatment as we call the microhydraulic. This component is raw water coming. We can also use the raw water from the high level with gravity system, or here with pump system also is fine. And the first process with dosing. With dosing system, we have a strict dose. One about the pH correction, the second about the prechloralization if needed, and then the coagulant after that, because we hope the pH here must be 7 before prechloralization and before coagulation. This is a coagulator. This is a flocculation, and clarifier, and then rapid set filter, and also disinfectant again. Yeah, the concept of coagulation, I still follow the von Smolsky. Yeah, they have still 1917, but important thing just only G. This is important thing. G is yeah, in between G is P per mu and per volume, yeah, power of hollow. This is the model of one model of the flow collision with labyrinth, and then also this is the rotator, yes. But two also is I think good, but for me is will be better to make more simple and more small of in the detection time. This is I make like this. I make they said maybe we can call colloidal because the first time I help and design the water treatment, maybe in Indonesia the name helicoidal. So many treatment plan now built by helicoidal flow collision. This is I will show you in the example. This is coming from yeah, the name the golden number, or maybe do you know Fibonacci? Yeah, Fibonacci. Okay. Okay. Now I want to inform you about the illustration of the coalition of the coagulation process.
Mr. Garsadi, sorry for interrupting you. How much time do you need for your presentation?
Okay, this is I will very fast. I will very fast. Maybe just only maybe yeah. I think 10 minutes or 15 minutes is fine.
I don't know if we have that much time. Looking
Okay.
also to the length of the other presentations.
Okay. Okay.
And I think at 10 o'clock a lot of people will leave the meeting, so then
okay.
It's not good for the other presentators.
Okay, I will very fast. Okay. Yes. This is the illustration of coagulation process. Yeah. Maybe. And now I try to make a microhydraulic laboratory model. This is our model. Is will transparent. We make a modeling laboratory in Delft University laboratory, and then you can see this one. Yeah, this is one column, and there's another column. We measure everything with ADV, acoustic Doppler velocimeter. Oh, this is so. This is also a big. Okay, this is also how I work looking. This is all many professors and many colleagues also help me, and this is very important. How to make the very good flow with very fast and then very efficient of the coagulant. This is I try to measure in everything flow in every position. Also this one. This is just needed decision time only in between 8 until 10 minutes. This is I show you this is the video how to flow collision working. Yeah, you can see this is every flow very gentle, and then every flow big aggregation. Yeah, okay, just fast maybe. Yeah, maybe I cut. This is also all professor. This is maybe from Faye, maybe meet the last director of Mr. Jan Hofer. Another also this is my professor. This is the reactor, our reactor. Yes. This is the mathematical model for the tube reactor, and then we find also relation between gradient velocity and then detection time. This is also my mathematical model for the column. You can see. Yeah, every position, every I measure it. Yeah. Okay. This is also I make another very small system. This for continuous jar test. This is also I try many model and many typical. Also you can see also it's very good flow. Yes. Now I'm going to the helicoidal mathematical model. This is maybe the first time I make a design a treatment plan. The first time this plan built in Bali. Yeah. and then the second around in Bandung, and after that, so many copy pastor with many people, many engineer in Indonesia, yeah, and public work also. But this plan still possible to upgrade and then to make better. Yes, this is, you can see, this is just working around here. Yeah. Another not really good, but this capacity may be possible until increase until 200%. Also, this one you can see. This is what I can say. This is some break up in the red one. In the red, okay, this one also. This is a break up. Yeah, this is also the possible of the process. Also, this is another model in the boxes. We can comparing. For me, this is more better. Yeah, more better than other. Also, this is for like a sample in Vietnam. Yes, this is also for UV system. Okay, now I have already also built and designed, and until now maybe more than 30 water treatment plant in Indonesia is already built. This one just a design. This is design. This is one plant in Makassar. The first I inform you, the water company ordered me, asked me about 75% liter per second, but now it's operation in between 140 and 150 liter per second with very good flow and very good system, and then efficient, and then also chemical consumption is very less. This is the flow chamber as the above here. This is another plant in the north of Jakarta I built for the seaport. Yes, it's very good, very bad raw water, but now is they said this is a food grade. Also this one in Bali, yeah, and also this is another plant in Sulawesi, and this is also designed for the campus of our campus of Institute Teknologi Bandung. Yes, this is I just show. This is a ministry of public work, and this is myself. This is the rector. Rector is rector of ITB. Yeah, we have built one first the plan for capacity about not too big, only 20 liter per second, yeah, for supply to area of the campus. And the second one also with the different ministry. After that, yeah, this is Mr. Basuki, the Minister of Public Work, and then this is Director of ITB. This is myself. Another thing, this is I build also not only in the steel or the stainless steel, also built in the concrete. This is I'm lucky I have tried. This is very clear in the clarifier. Also this one for this is a little bit pit water in the Kalimantan, and then the result is very good. Yeah. Oh, this one also. Okay. Also here I make also a plan for emergency with capacity only about 200 and until 400. This system is same with the first system I inform you, but I add here the filter about the GAC filter for the treatment plant, yeah, granular active carbon. This is my prototype, yes, already tested and then already certified and then already patented. Yeah. This is during the flooding in Jakarta. Also, this is we have a cooperation with medical doctor of association, yes, and then you can see many people needed water, and then he is very happy with the very big flow and then very clear water. This is also, you can see, this is the raw water coming. This is the mobile plant. They are really needed water. This is also we use the plant for the internship of a student, or student also for research, and then also for training for water company. This also many people from government coming for looking And also, this is the first time I build and sending to the tsunami in Aceh. This is the plan, and then working well. Just only operate by the army, and in 3 or 4 hours they are already operation. This is also in Aceh. This is also training for the army. This is also the flood water in area in Jakarta and around. You can see also here this water company in Jakarta. We help with the products from the water treatment plant mobile. The quality is more better than the real plant. You can see here. We can treat the water, the same raw water from water company. We found here is 0 NTU, and then the the TDS about 111. Sorry, 118.
Mr. Garsadi, may I ask you kindly to finish your presentation,
Yeah,
because
okay.
otherwise there will be no time for the other presenters
Okay.
as well.
Okay. I just the
I think
last thing.
I think there are a lot of examples, and
Okay. The last everything I have already present from the Ministry of Research and Technology in the year of 2014. Okay, thank you very much for time for me.
thank you very much, Mr. Garsadi, and explaining your concept of a microhydraulic water treatment plant. And I think you can you are able to fill a complete webinar on your own. I have no doubt on that. But looking at the time, maybe there is time for one quick question. And if there are a lot of questions, you can put them in the chat, and maybe we can forward them to Mr. Garsadi as well. Does anyone have a question to Mr. Garsadi? No one dares to ask questions anymore, I think. Yes, Adrian.
Yeah, thank you. My name is Ardian, and I'm from Indonesia also. I'm from Semarang. And I've read your article, Pak Rusnandi, regarding your article of microhydraulic. It is very interesting, and it was nice to be able to hear it directly from you in this session. And I will also to explain and ask question. Currently in Semarang, we're also conducting some activities to improvement in improving the reliability of our water treatment plant, mainly because of the extreme turbidity that happens during the rainy season. Because in the rainy season, the turbidity can go as high as more than 10,000 NTU. And my questions are, number one, does microhydraulic can help to treat the very extreme turbidity? I see that also in your presentation that microhydraulics can help in treating high turbidity, but how high is it? For here in Semarang, we usually stop our production when it's reached around 10,000 NTU. But in the river, the level of turbidity can go much more higher than that. That's my number one question. And in number second, in the end, the management or the directors also interested in the financial aspect when making an investment. And I also understand that from your presentation that the microhydraulic can reduce the coagulant usage, but also based on your experience or based on the pilot that you already conduct, how long does it take to break even? Because it's also interested that if, for example, the investment is not too big, then a small scale for the work, for example, in the waterworks, can also take place as an initiation that so the partner utility can also invest more in the bigger scale. So that's my question. Thank you.
Okay, this is I can answer directly. Hello. Yes. Okay.
Yes, please.
Thank you very much, Pak Adrian. This is really nice. Semarang. I have been built a plan in Semarang in the front of your office. Yes, that is my design. Yes. At the time, the capacity design about 100 liter per second, but now running, I understand, 250 liter per second, right? Okay. And another plan is in Kudu. Kudu I built with Iwako, BV. I built in there about the capacity of 1,250 liter per second. Yeah. That is by the technology that is very old technology. Now I can make the treatment more better. Maybe the capacity will be double, and the coagulant also will be less, and the turbidity is no problem. I have already try the turbidity until 2000 or more, still possible, but you need additional of the coagulator system. Yeah. And then the second one about the financial, I think the financial, because the plan, this is really will be double capacity. Yes, of course, will be if you have let's say for break-even time, maybe let's say it's normal is 10 years. Maybe for microhydraulic will be less. I try maybe just only 3 years is break-even. This is you can maybe next time I'm in Indonesia, we can discuss with your director. Thank you very much.
Yeah, looking forward if you have time to come to Indonesia. Thank you for your answer, Pak Rusnandi.
Okay, thank you very much. I see there are some questions in the chat, but I think Ashmead, you have the possibility to forward them later to Mr. Garsadi, because I think there is no time for these questions anymore. And I will give the floor to Vin for his presentation. Please, Vin, your presentation and introduce yourself.
Thank you, Mr. Jantinus. About the question of Adrian from Indonesia, maybe in my part, I will share our experiences with microhydraulic in Vietnam. I will also share a little bit about the investment costs and the savings you will have with chemicals by applying this solution. Please let me share my presentation.
Yes, it is in the presentation mode, Vin.
Okay. First of all, I want to. We are very grateful to cooperate closely with Mr. Rusnandi on the microhydraulic technology. As you can see in his presentation, it took a long time, a lot of effort, a lot of studying and testing to get to this solution. For us, it's more simple, and the solution already is there, so we just implement it here in Vietnam. First of all, I would like to introduce myself. My name is Vinh Ngo. I'm director of Vietnam Joint Stock Company. Today, first, I would like to introduce a little bit about our company, what we do in Vietnam within the drinking water sector. Second, I want to shortly go through the water challenges here in Vietnam, which I think can be the same in many other countries. And finally, I want to share our experiences with you by implementing the microhydraulic rehabilitation and upgrading projects in Vietnam. We have applied several projects here in Vietnam, and the conclusion is the results are very successful. So I would like to share the results with you about these projects. First, what we do in Vietnam. We are located in Ho Chi Minh City. We are active in 3 fields within the drinking water sector. At first, we are a water utility, Holland Water Supply Company, supplying safe, reliable, and affordable drinking water to 10,000 households and some industrial parks in the Mekong Delta. It's in Cang Du City, Long An Province. Here we extract groundwater and we apply Dutch technology to remove iron and manganese without chemicals. We are operating and do the maintenance ourselves since 2005, and we are a private water utility. Besides, our Holland Water brand produces bottled drinking water. We manufacture purified water and alkaline water. And finally, Penang Joint Stock Company is our EPC contractor company specialized in drinking water systems and water treatment plants. The microhydraulic technology that we are talking about today is done by our EPC company, Penang. So I would like to tell you a little bit more about Penang. Penang is a Vietnamese EPC contractor in the field of drinking water. We are experts in ground surface water and packaged water treatment. Besides EPC is our core business. The majority of our projects are based on EPC contracts, but we also can cooperate based on turnkey or even co-finance based on BOT or BOO. Performance-based contracts are also possible. This is mainly in the field of non-revenue water, but also possible for microhydraulic projects. So, like for example, the chemical savings that you achieve. The investor can pay back within a short amount of time. Besides engineering and construction of water treatment systems, we are also active in the field of non-revenue water, operation and maintenance, SCADA, and other consultancy activities from tap from the source to tap. That's because we are also water utility, and we have experience with all these activities within the drinking water sector. Throughout the years since 2010, we have done many projects in Vietnam, mainly in the Mekong Delta, as you can see here on the right. Shortly about water challenges in Vietnam. Of course, unfortunately, there's the climate change, a big climate change impact also in Vietnam. Salinity, intrusion, organic matter, pesticides, residues, etc. Mainly, especially in the Mekong Delta, where we are active. Land subsidence is a big, major issue because of the groundwater extraction. The water tariff is very low. Set by the government, and in the last years there's less ODA coming to Vietnam because Vietnam is seen as a emerging country. To tackle these issues, there's government policy at this moment to remove from groundwater and look for alternative water sources like the surface water. The government policy is also privatization of the water sector. Yes, but if you want to attract private sector, then you have to have efficient solutions and innovative solutions, and that is where the microhydraulic technology can support, can be part of. About the microhydraulic rehabilitation and upgrading projects in Vietnam. Rehabilitation and upgrading, can be very diverse. The scope of work, it really depends on the existing system. The main part, the heart of where we focus, just like Rusnandi explained, is the coagulation and flocculation part. We think if that works very efficient, then the remaining steps needs to work less hard. So we focus on a small footprint. Reduce civil works as much as possible. We also focus on chemical efficiency. There's less mechanical parts, So maintenance will also be less of an issue. Those are the main focus points of the microhydraulic technology. One project, rehabilitation and upgrade project, it can be from intake to distribution system. Normally, you will need to replace the pumps with high capacity, maybe increase the dimension of the inlet. The calculation and flocculation part, the microhydraulic is basically equipment. So there's the multi-point injection, the first part here. It's like a static mixer. Optimization of the static mixer. We have the mixing towers, that's from steel or stainless steel. And the calculation, flocculation part, there are the stainless steel flow drivers, in which we minimize the civil works, concrete works, as much as possible, and only install the equipment like the flow drivers. Some projects we also have to need to rehabilitate the clarifier, like for example install lamella tubes, and sometimes also the sand filter, maybe replace the filter material or add Leopold filters, for example. So each project is very difficult. Yeah, that was the question of Adrian also. It depends on the existing system to estimate the investment cost of a project. Yeah, in Vietnam, there are still many big old concrete systems based on old technology. So the market for rehabilitation and upgrade, like microhydraulic, is big here in Vietnam. And yeah, from the investors' side, yeah, with microhydraulic, you can have a lower CapEx cost. You can reduce your operational costs. So why not rehabilitate and upgrade instead of building a whole new water treatment plant, which also you need maybe extra land for that. I would like to share with you the results of the projects that we have done here in Vietnam. Our first project was in 2016. That was in An Giang, Ba Chúc, that's near the Cambodian border in the southwest of Vietnam. This water treatment plant was very small, 400 cubic meters a day, but the structure was huge. It's 8.4 by 4.4 by 6.2, 25 meters. So because of the existing structure, it was very big. We were able to upgrade the capacity within the same structure with 6 times the existing capacity, from 400 to 2,400 cubic meters a day. Besides the chemical dosing of PAC, we reduced from 21 gram per cubic meter to 9. So that's a huge improvement for the water utility. And of course, the water quality after the sand filter was according to the drinking water standards in Vietnam. The NTU from the raw water in this location can be maximum 500. NTU after clarifier was under the 500 NTU, and after sand filter under 2. Besides, we could also reduce the backwash water frequency from 24 hours to 30 hours. So we could improve the backwash cycle a little bit. So this is also cost benefit for the water utility. Second is a microhydraulic project in Bến Tre province. That's in the Mekong Delta, close nearby the Ho Chi Minh City. Here we upgraded the existing water treatment plant from 1,200 to 2,400 cubic meters a day. That's 2 times the existing capacity. within the existing structure. The chemical dosing, PAC dosing, we reduced from 18 gram per cubic meter to 8, so more than double. And of course, also here the water quality was very good after the treatment. Here we could improve the backwash water frequency more than in Anyang, from 24 hours to 36 hours. We also upgraded, and this is a bit larger capacity in Tay Ninh province, as in the west of Ho Chi Minh City, also nearby the Cambodian border. Here we upgraded the existing water treatment plant from 9,000 to 21,000 cubic meter a day, and so more than double. And we reduced PAC dosing from 19 to 9 gram per cubic meter. The NTU in this raw water, the surface water, was not that high, only 100. So NTU after clarifier, we achieved under 2, and after sand filter under 1. Because NTU is not so high here in this location, we could improve the backwash water frequency from 24 to 48 hours. The fourth project is in La Ghi, that's a coastal province in Vietnam. Here we upgraded the capacity 3 times, from 5,000 to 50,000 cubic meters a day. Within the existing structure, 28 by 13 by 4 meters. We were able to reduce the PAC dosing twice, from 60 gram per cubic meter to 30. NTU in this location can be higher, 2,000 NTU, and after clarify the NTU is below 5, and after sand filter 2, the backwash water we could reduce, we could improve a little bit with 4 hours. I can show you a little bit more detail about this project. At the left, you can see the existing structure, the existing mixing tank, and the flocculation system before rehabilitation. And at the right, the green letters, it's after the rehabilitation and upgrade from 5,000 to 50,000 cubic meters a day. Here we have replaced the existing concrete mixing tank for the microhydraulic mixing tank and the multi-point injection chemical mixing to improve the mixing system. And we have added flow drivers and also very small changes in the concrete structure. And we installed the flow drivers plates to improve the flocculation system. Secondly, we have added the honeycomb lamella tubes. And at this moment, the water utility is also looking to rehabilitate the sand filter by adding Leopold HDPE filters, but only with until this point, the clarifier, we already achieved the upgrade from 5,000 to 15,000 cubic meters a day. So the water utilities are very happy about that. With microhydraulic technology, we can also build new water treatment plants, and so it don't have to be rehabilitation. Here in Bến Tre province, in Mekong Delta, we also built a new water treatment plant of 5,000 cubic meters a day 2 years ago. Compared, because there is an existing water treatment plant next to the new one, and compared to the old water treatment plant, the chemical dosing is a little bit better, from 15 grams per cubic meter to 10 grams per cubic meter. NTU here is 300, can be 320 NTU in the raw water. After clarifier below 2 and after sand filter below 1. The backwash frequency improved a lot compared to the existing system, from 24 hours to 72 hours. This is a project case in Ninh Hoa, also coastal area in central Vietnam. Here we built a microhydraulic system from steel. This was originally a design made by another consultant, but because it was not optimal, we were able to add the microhydraulic part in this design. The total capacity of this project is 6,000 cubic meters a day. The PAC consumption is from 10 to 15 grams per cubic meter. NTU in groundwater can be up to 700 NTU, after clarifier 5, and after sand-filled 2. The backwash water frequency is a little bit fast, 14 hours, but that's also because of the original design. It's a self-cleaning filter design. If it was up to us, we would do it. We would design it differently, and I'm sure the backwash water frequency would be longer then. This is a new project that we are working on now, also made from steel. This is our own design. The capacity is 2,000 cubic meters a day. The chemical dosing we expect PAC is only about 10 grams per cubic meter, and backwash frequency we expect to be 48 hours. This plant is in the Mekong Delta also, and we will commission within 2 or 3 months. Besides, we have also made a pre-feasibility design, pre-design of 30,000 cubic meters a day water treatment plant in the Mekong Delta, just to show that with microhydraulic technology, it can be small, so mobile systems, like Mr. Rusnandi just presented, emergency systems, but it can also be big. Like this module of 30,000 cubic meters a day. And this is also preliminary design in Dalat, central Vietnam. And this is a rehabilitation upgrade project from 25,000 to 60,000 cubic meters a day we are working on now. So you can see that it's a different design, cylinder, and so it's applicable for a lot of existing technologies. This is a summary of the projects that I just presented to you. I think the most important thing is that about investment cost, it depends on the existing system. The scope can be very big, from intake to the clean water reservoir, but it can also be only the process unit or the coagulation part. It really depends on the existing system. But here, for example, you can see like in Binh Chea, number 5, a new water treatment plant of 5,000 cubic meter a day. The investment cost is about $100 per cubic meter water. But rehabilitation and the upgrade project in Binh Hung, the investment cost is half, $50 per cubic meter. You can also see in this table the chemical savings per year. Of course, the bigger the capacity, the more efficiency, the more savings you can make. For example, in Binh Hung, we upgraded from 5,000 to 50,000 cubic meter a day, and the water utilities can save $47,000 per year. So I think that's very beneficial for the investor. To sum up the benefits of the microhydraulic technology, the investor, the water utility, can save a footprint, so you don't need to build a whole new system. You can use the existing structure. You can save construction time, and the investment cost can be lower than building new, up to 2 times compared to building new. You can save chemical consumption. and there are less mechanical parts using. For example, in the flocculation part, so the maintenance can also be easier and be less. And safe backwash water is also a big advantage compared to building new. These are the cases in Vietnam since 2016. There is still a huge market here in Vietnam.
You are muted, Mr. Vinh. You are muted. I don't know if that is done by. You are still muted. I don't know what's the problem.
Can you hear me now?
Yes.
Okay. 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 Thank you. So basically, these are the results of the microhydraulic technology in Vietnam. I think there's still a big opportunity to develop this technology here in Vietnam, but also in other countries. My name is Ngo. I was born and raised in the Netherlands, where drinking water is common. I'm happy to be here in Vietnam since 2010 with our companies, and together with Rusnandi, we are trying to contribute to a better, safe, and affordable water access in Vietnam, but hopefully also elsewhere. Thank you.
Thank you very much, Mr. Vinh, for your nice presentation, explaining a lot of examples from practice. Looking at the time, there is no time for a question, because I will give also Joseph the floor for his presentation. So if you have any questions for Mr. Vinh, please put it in the chat. And I hope that we can have also all presentations to put on Workplace to look at it, and hopefully the presenters will allow us that. So Joseph, I will give you the floor for your the last presentation.
Thank you, Yantanis. Thank you, colleagues who are attending and organizers. I want to believe you are seeing my screen from your end.
Yes, you have saved the screen, Joseph.
Thank you. I will introduce myself briefly, and I'll try to keep my presentation in the next 10 to 15 minutes maximum. So bear with me if I go a bit fast. I want to make sure we are not losing time for the guests we have invited in this webinar. My name is Joseph Tweheyo once again. I work for National Water and Storage Corporation in Uganda. I am also currently the plant manager at the new treatment plant called Katosi. That's a local name, don't mind it. And I also double on this GeoPA community as a moderator for the CoP water production. So I will take you through a complementary presentation sharing the case of Uganda, the National Water and Storage Corporation in Kampala, just to share with you our experience in terms of the challenges we faced, and of course, what we did, the interventions we did to ensure that we get the plants upgraded and cope up with the kind of raw water we had at the time. And of course, it is even getting worse, but at least we're able to cope. So just before I leave this page, this is quite a view of the treatment plants I'm talking about. In the fore, you see Gaba 1. This is the first plant we'll be talking about. And at the background, in the middle there, you're able to see other blue structures, blue and white structures. That's where Gaba 2 and Gaba 3 are located. And in the far background, that is the residential area, but of the Kampala city, which is a little bit more in the center of that picture in the background. And also you can take interest in the kind of water we have. This is Lake Victoria, but as you can see, the water can be green because of too much organic matter. So quickly, this is the agenda for the presentation. I'll try to show you a little bit of background information about National Water and the project itself. Then I'll take you through the challenges we were facing at the treatment plants in Gaba before we did the rehabilitation and upgrade. And of course, then share a little bit more in detail the interventions we had to deploy to ensure we cope up with the circumstances we were going through. And of course, in brief, I'll also highlight to you the benefits, but mainly we shall talk more about that in the interventions. And of course, at the end, if we have time, we should be able to have the question and answer session, but it will be depending on time. So fast forward about the background to National Water, for those of you who are not aware of National Water. National Water and Sewage Corporation is a government of Uganda owned parastatal that was formed in 1972. And it has a mandate to supply potable water and sewage services to all urban centers in the country, as long as they are gazetted by government to be operated by this entity. And currently we are operating in about 273 towns in Uganda. Of course, Uganda has more towns, but those are largely more smaller towns which are directly handled under the line Ministry of Water and the Environment. But the bigger towns are largely under national water as per the government gazettation. Now, Kampala City is our capital city, and it's the biggest of our operational areas. We call them areas, so the towns you see up there are also areas in our terminology here. So this Kampala City, where I work, accounts for about 60% of the national water business. It's the capital city, it's a metropolitan city, and it has the biggest business within Kampala, in Uganda. Of course, piped water. Kampala is the luckiest city. It is just located on the shores of Lake Victoria. So we have all the water, really, I would say 99% of the water we use in the city is abstracted from this Lake Victoria. And of course, treated at the 4 different treatment plants we have in the city. We have Gaba 1. This is the oldest plant that was established in 1930, the time of colonialists. And the Gaba 2, of course, as the city was growing, came in around 1992. And these 2 plants are the ones I'm going to focus on in the rehabilitation and upgrade project we did. Gaba 3 is a little bit newer, I would say 2007, about 15 years plus now. And of course, the Gaba Cato C, the current plant I'm currently managing, is just a recent one. And it was a little bit of different technology, which I'll also touch a little bit at the end of the presentation. So that's a little bit of that. And to highlight you how the city is located and how our supply coverage is in terms of water supply. In the lower corner, you're able to see we have Lake Victoria, but this is really a smaller part of Lake Victoria. Lake Victoria is the biggest fresh body of water we have in Africa. And where we abstract water here in the lake, it is basically it's called Ngo Bay. It's a small arm of the lake. And this is really also, if you look at it geographically, it is quite locked. So it is not an easy one to refresh. Much as we have a very big water body behind here, this is purely a locked kind of section of the lake, and it has also an effluent channel from the city. So the challenges are really already coming through from here. And of course, this is how far we cover the supply network. We have the central business district of Kampala here marked with red boundary. We have another neighboring district called Wakiso in green boundary. And then we have the boundary of Mukono district, which is on the east of the city. And the new treatment plant now is also on this side of the eastern side of the city. But quickly now into the project, the little bit of background of this project. The rehabilitation project we did for Gaba 1 and Gaba 2 is a section of the bigger project. It was codenamed Kampala Water Lake Victoria Water and Sanitation Project, which has 7 components. And these rehabilitation projects I'm going to talk about are only for these 2 components highlighted in red. But National Water, being as it is, it has the government support, but also it has established itself as a very commercially viable institution. So we were able to get a consortium of development partners supporting our project. And these various agencies were able to come in handy to give us loan and also a grant facility, which I will also just delve into a little bit more here. So this very particular section 1 and 3 of that project was done between June 2014 and July 2016 for Gaba 1 and Gaba 2 specifically. And earlier on, we had a smaller phase note that actually triggered this bigger project to come through. I'll also talk about it a little bit because it was already done just before this very bigger project, but it was in line with the same changes we're facing. The project costed us about 43 million euros, and it was jointly funded by the government of Uganda, KfW, the French Development Agency, and the KfW and the French Development Agency gave us a loan to the government, but the European Investment Bank gave us a grant facility. So this joint funding managed to make this project a success. And of course, they are still doing for the other packages, as I told you. So it's quite a big funding in total, but this is only what I'm going to focus on. For the project to succeed, we had to procure a contractor. That was Sogea Satom. It's a French company, currently I think taken on by Vinci, if you know that name. And of course, the consultants are from German, called CES Consulting Engineers. So in this slide now, I show you the challenges. I try to use more pictorial to explain properly what really was happening or what is even still happening somehow. If you look at the pictures, of course, I list 5 major challenges we're facing. You can read through, but I'll try to talk through the pictures. The lower left picture, this one here, is where I start from. If you look at this picture here, in this country, we have this water body, very big as it is, and it should have fresh water indeed. So at the time we established this plant, this is an intake for Gaba 1. That is 1930. The treatment process was basically pick the water from the lake as clean as it was, filter it, disinfect, and supply to the city. That time it was even a smaller town, I would say, not even a city. But this facility has been running with this intake up to the around early 2000, maybe the early 2000, but I would say specifically 2008. But as you can see, because of the pollution that was happening in the lake, as I had mentioned earlier, the lake is already having a section that is not very easy to clean, to rinse, because it's not easily cleaned by the waves. We have a locked section of the lake, and that's where we are obstructing from. But in the same section, we have the industrial effluent and any other effluent, they run off from the city, entering the lake. So if you realize now the top picture, it shows you the kind of organic matter we usually have in such a lake. The green layer here you see, on some bad seasons of the year, this would be the kind of raw water we have, a bit of green soup, if I might use that word, entering into our treatment facilities. And at the time of designing, both the 1930, which was actually upgraded around 2004, and the one which came, sorry, the 1964, we get the biggest upgrade of Gaba 1. Then we come with 1992 Gaba 2. The same quality was still not a worry for us. Now, these 2 plants also were established with not all the stages you would consider in a conventional water treatment plant for surface water. So again, we have a challenge of the shower, which is, I mean, the intake being closer to the shower, where the organic matter is being deposited. And of course, if you look at the lower picture again, on the left, you see there is a plant in the intake here. This plant is called water hyacinth, and when it is brought by the waves on the shore, it breaks and it decomposes, and of course contributing to the organic content we have here in the lake. And as you do the treatment, applying quite a big dose of chemical, you also get, you can see this is at the mixing chamber, you have about a little bit of green scum. So we are having seasons where we could not even treat water. We have to switch off and first clean the system. And of course, even if you struggle to treat, you are going to treat less volumes, and it would not also compromise on the water quality because of the inefficiencies of the stages you have. And in the long run, you have less water being supplied in the city, but also you have water which has poor quality. Not necessarily poor, but it's really compromised quality. It will always pass microbiology, but when it goes to physiochemical, you definitely not get it to the standard. And of course, we had high demand. The city in the 2000s was already big, and we had a lot of people in the community. So we had to supply more water, but we're having a challenge. Okay, so quickly going forward now, I highlight to you the interventions. The first part of the project and upgrade we did was to use, first of all, you can see properly here from this picture, you have the intake close enough to the shore. And with this green water almost everywhere, you would have this water coming, and this intake was also a little bit shallow. You would have it bring in a bit of green water, difficult to treat with a lot of organic matter, and it couldn't go through the stages. And of course, even if it went through, it would compromise on the water quality, choke the filters. So the first phase of the project, done a little bit earlier before this major project, was to do a new intake. A new intake run away from this shallow and near the shore intake, create a new intake further away from the shore, but also deeper, so that if you have green, this usually is a lot to do with algae, which comes because of the sun effect. So we had to do a new intake station that was now far away from the shoreline, about 530 meters, but also deeper. It was about 15 meters below the surface of the water. And that would guarantee us a little bit of regular and stable kind of water quality, which was cleaner, to be treated across the year. And of course, that helped us also to manage the water, the chemicals we're using to treat the water. In this case, we're able to benefit in terms of cleaner source, but also effective treatment in terms of even the chemicals being used. Then, of course, this intake was done for all the 3 treatment plants. I just have to mention that. It was not only for one plant, it is done for even the other two plants. So it was a common intake for the three, yet they had different smaller intakes which were a bit closer to the showers. Now in this project, where we do upgrade and rehabilitation of the treatment stages, and of course trying to cope with the current raw water quality we have, we had a number of studies, of course, were done by the consultants, and it was agreed. I'm going to be brief on the benefits and what we did in particular in a practical sense, not to go into the detail of what was designed and all that. It was agreed because of the green water or the would-be organic matter in the water, we had to cover all our treatment stages, the clarifiers or the sedimentation tanks, and also the roof was put also on the sand filters. At first they were open, but because of the sun and the water content having a lot of organic content, the raw water would treat the water at the coagulation and filtration stage. But again, we develop algae in the stages as we go further to treat the water. So we had to minimize that effect by putting a roof on all the stages, which were open to the sunlight. But also in detail, we were able to introduce lamella plates. I saw in the previous presentation, you would see some sections had lamella plates. It was also initially designed that these were open, flat bottom sedimentation basins. And the sludge, after doing the chemical application, the sludge was not easy to settle. You'd have it, what we call carryover. You have carryover from the clarifiers. So what we did was to introduce lamella plates. These lamella plates, if some of you have not seen this technology or these units, they are hexagonal in shape for our case, and they increase the contact surface. So as the blanket of water, the sludge blanket comes up in the clarification stage, it gets more areas or more surface area to get in contact. And only clear water now will come through, leaving the bulk of the blanket and sludge below the sludge blanket. They are suspended, below the lamella plates, which are suspended halfway into the clarifier basin. And of course, we also introduced recycling in an effort to improve the efficiency of the treatment plants. We are aiming at getting more volumes being produced from the existing facility to supply to the community, which had now increased in demand. So we had to also introduce recycling, both for the sludge water 100%. Sludge water here is the case of backwash water, and then the sludge, because the sludge we're doing only about 30% of it. We're able to recycle this to improve on our efficiency and increase the water we could produce. In the earlier stages, our filter sand media had been clogged with a lot of organic matter, and it was really not good enough. So it was also planned that we replace all the sand with, of course, properly graded sand that could easily allow filtration to take place and, of course, increase the filter run hours. And I think in the results, we were able to come from about average of 14 hours to about 28, 30 for all the treatment plants. So that was also a big benefit. But also to ensure that we minimize the effect of human error and, of course, anything that can come along with the human being trying to operate a system like this, as complex as it is, we had to automate the plants using a SCADA program. So this also helped us to improve the efficiency of processing the water. And of course, in the long run, at the end of the day, for this particular plant, GABA 1, we envisaged that we are going to have more water being produced. And we had to establish now another pumping station, additional pumping station that was able to evacuate for us. And where on average it was doing about 33 because based on the demand, but it has capacity to pump up to 50,000 cubic meters of water per day to a dedicated side of the city. Because again, this was to help with the supply challenges we were getting in the network. So this plant had to receive the new the new pumping station that would be able to deliver water to a certain area of the city that was constrained regarding the water supply. Now, on the final side of this intervention and what we benefited, the other part was GABA 1, which I was showing you, but some of the things were also done in GABA 2. In this slide, I also highlight to you what we were able to do. For GABA 2, this is GABA 2 treatment plant. Initially, it had only abstracting the raw water, pass it through a small chamber, call it a flash mixing chamber, of course, after applying the chemical, and then take it straight away into the clarifiers. But we noted from 1992 that was okay. But as we crossed into 2000 and we had that too much pollution in the lake, we couldn't handle the treatment of this raw water. So it was planned in this upgrade and rehabilitation that we introduced coagulation and the filtration stage that would be able to help improve the way we treat this water that we are currently having. And as you can see here, We also introduced lamella plates. These are just lamella plates in the middle of the clarifier basin, suspended, and that way you have all the blanket remaining down there, the sludge below, and the part of it will be trapped in the lamella plates. Then the final waters you can get a bit of less than 5 already here, but we of course have results as you can see here. If you look at these graphs in GAVA 1 and GAVA 2, GAVA 1 is red, GAVA 2 is the blue. You see we had color of average, this is final water, remember? We're treating color of average maybe, I would say 20. But as you can see, after doing the rehabilitation and upgrade, we're able to go to an average of about 7. And this was able to help us, of course, meet the standards, both on the bacteriological, but also the physiochemical, microbiology and the physiochemical. Now, when it comes to GABA 2, the same. It was hardly meeting the standard of 15, but as you can see, it averaged up to about 5 PTU. And for the turbidity, the same. It was already meeting for final water, but of course, not really very good. So we had to further improve it. And this adds to the other benefits of improved volumes we got. And of course, the benefits, as I had mentioned, I want to summarize them for you here. We were able to get a cleaner source as a result of this upgrade and the rehabilitation of the plants. We also got improved efficiency for the entire treatment process. And of course, this resulted into more water being produced for the community, up to a tune of about 15% overall from the 2 plants. And this helped us, of course, bridge the gap of the demand we were having. And of course, along the way, we also got a modern laboratory. This could be thought in the rehabilitation project, you have to think a little bit outside the processes. Yeah, the lab that had been established in the 1992 was really not very big enough. So we had a modern laboratory with a modern equipment that was established to test all the parameters of water at the plant itself. And of course, we had the water that was going to the community much, much improved. So those are the benefits we got out of the treatment plant rehabilitation and upgrade. Now, again, just highlight for one slide, this is the last slide. We had still, as you saw, the water quality was not yet very perfect. We love to see the color 0. We want to see turbidity less than 1. But the other plants, after the rehabilitation, still had some constraints. But also, the thinking was that we had to do more because the demand was still not being met. We had an estimated demand of about 300,000 per day, but actually we're only producing about 240. So we had to think of a new treatment plant on the side of the Kampala East. But in this treatment plant, of course, the lake is a bit more cleaner in this side of the city. It's not a locked side of the lake, but also it's a little bit not developed. It has not much of a lot in the catchment area, if I might say. Now, we noted that our water here was slightly good in terms of raw water. And in our search, we have also got another technology. It's called dissolved air flotation, where we are able to treat this water whose average is about to, the turbidity is average. It's actually less than 10, but even if it goes up to 15 or slightly above 20, you are still able to manage, but it shouldn't be constantly high. So for such freshwater bodies where you have turbidity a bit low, this other technology has been now employed. And in Uganda, it's now being upgraded after testing it for this treatment plant where we are having this technology. It is producing 160,000 cubic meters of water per day. That's big enough. And we have tested it. We seem to like it. It's a very compact system, economical to build, but it's also very efficient. Where you are supposed to treat water in a clarification stage, where you need 1.5 hours to have the water pass through very big basins. Here we are treating water in the space of 8 to 12 minutes. The water is coming out of the clarifier stage, which actually is the DAF, and you have small units which are easy to construct in terms of economics, but also if you have a small space, this plant can fit in, but give you bulk volumes you need to supply to the community. So this is the current technology we are currently going with, but it is new technology and new plants. We have only tried a small section of it in the Gabon treatment plant to improve the clarification because we noted the clarifiers were quite small. They were not able to give us the volumes we wanted. And as such, we were able to get the section of 1 unit done at Gabon. And now the 2 plants have been tested on this system of this technology. And we have been able to get very good results. And that's where we are now moving forward as Uganda, where we have freshwater bodies. This is the new technology we are going with, which is a little bit more advanced compared to the clarifier stage. I want to thank you so much for listening. I want to believe I've been in time, Young Tanis. And for more details, of course, regarding this technology, the new one or the interventions we did before in the rehabilitation, please reach me on my email and my phone. If you really can, this is a phone which is also on WhatsApp, so we should be able to be in touch whenever we can. I want to thank you so much for listening.
Thank you very much, Joseph, for your presentation. Very nice to see also how rehabilitation of a water treatment plant can improve water quality as well. So we are running out of time already, so I will make a small wrap up before finishing. First, thank all the presenters again for their very nice presentation. And I think this is a very nice way to exchange knowledge about water treatment. And it was for me also very nice to see that the knowledge which was obtained by universities was also implemented in practice, as we saw from the presentations of Rusnandi and Vinh, of course. I think this is, in my opinion, very nice webinar. And I will also announce the next webinar, and that will be on July the 12th. And maybe, Caroline, you will maybe give a bit more information about that webinar?
That's okay. There's a nice flyer also, Ashmeet had it. We are going to form a presentation on the 12th of July. It will be a co-presentation by Yuljun Salada from COWD from the Philippines, Cagayan de Oro, Miriam Banda from CRWD in Malawi, Lilongwe, and myself. Yuljun will share the way the water safety plan is implemented in Cagayan de Oro. Miriam will tell a little bit more about the challenges they have about making the water safety plan and also at the same time trying to implement it. And I'm doing a little bit about the theory. So that will be on the 12th of July.
Thank you very much, Caroline. Now, I think we will finish this webinar. As I told before, there are some questions in the chat, and I saw also already that some of the questions are answered already, but maybe the questions which are not answered can be forwarded by Ashmeet to the presenters. So finally, I will thank all the presenters for the presentation, the audience for the attendance, and then we will end this meeting, this webinar, and I will ask the co-moderators and Ashmeet to stay in this webinar. We can discuss it. Thank you very much, all.
Thank you, and thanks.
Thank you for organizing this webinar and for listening. Bye-bye.
Bye.
Bye.
Goodbye. Thanks a lot.
Everybody is leaving now a little bit.
Yeah, I was about to unpack. I'm running to a meeting, but I will listen in a few minutes. No worries.
It's only a few minutes, I think.
Sure.
Yes. Is everyone no?
Not everybody is yet out. Yeah, still 3 people attending.
Because I want to discuss a little about the organization, of course, about this webinar. What was good? What was?
We also can postpone it to our next meeting, but
yes, that's also a possibility. But when it is fresh, I think it's better to discuss it. And I think, okay, I think one of the messages that we have to make clear appointments with the presenters to discuss how long presentation might be. I thought it was discussed, but okay, maybe it was not clear enough because as we discussed also maybe before, professors and people from universities, they